Good morning, one and all, Honors Physics students, to another edition of Honors Physics. It's Mr. Finn coming at you again from neighborly Northville with another physics lesson, this time on the definition of an electric field and maybe how we might use that with regards to Coulomb's law. Now, before we get started, guys, just had a couple of announcements. Things are changing rapidly. You may have gotten an email about the continuity plan given out by the school for the remainder of our time together, remainder of the year. Now, the live sessions, since I'll be making videos, doing my teaching through the video segments as we've been doing, our live sessions for this class will be Thursday mornings. We're going to go at 11 a.m. Thursday morning, 11 a.m. for live sessions, well, basically on a Google Meet. Now, I'm required to have office hours. So my office hours will be for the previous 30 minutes before the Google Meet begins. So, if parents need to contact me, or if you just need to email something in you'd like me to discuss on the Google Meet, please do so with the 30-minute window before 11 a.m. So my office hours for Honors Physics will be 10:30 to 11 on Thursday morning. Once again, this corresponds with 5th hour, and then of course the 6th hour would be the Thursday afternoon. But that should get us started. Now guys, for the electric field definition, let's talk about an electric field. An electric field is surrounding any charged object of any kind. But a lot of times we talk about a point charge, any kind of point charge. Let's use this pen, for example, this marker. Let's say the top of this marker was charged to 15 coulombs of charge. If it's positive charge, that means that there will be an electric field extending radially out from this charged point in all directions. If it were negative, there would be electric field lines extending into this charged object. So all charged objects, whether they're positive or negative, contain their own electric field. An electric force field surrounds any charged object whatsoever. An electric field is a vector. Therefore, if you have two charged objects, like a positive charge and a negative charge, there would be a net electric field between those two charges. The net electric field would be the result of this field and this field. So I'll show you this on the board, and then I've got a demonstration on a computer simulation that I'd like to show you as well today. Okay? Let's go to the board for a second. Okay, guys, let's take a look at electric field for a minute. An electric field surrounds any charged object whatsoever. So, if it's a battery in a circuit, that would construct an electric field because the battery would be a charged object. However, we're going to look at point sources just for a few minutes. So we'll look at an electron or a proton, or maybe a group of electrons or a group of protons. Sometimes you'll hear me refer to a ball of charge, and we'll put a number to that. Electric field is defined as force per unit of charge. So how much force does this charged object produce at various points? Force divided by charge. Now, why is it various points? Because force, as you'll remember from Coulomb's law, is kq1 q2 over r squared, or d squared. kq1 q2 over d squared. Now, that's the numerator of the electric field definition. So if we divide that by the charge of the test charge that we're looking at, we can see that Q1 is going to cancel out on both the top and the bottom. And we're left simply with K Q2 over R squared. Now, what is Q2? That's the charge that we're speaking about. So, if we remember, we talked about the head of this marker being a charge. Let's say 15 coulombs of charge. Okay, so there would be a force associated with this charge at a certain point. The electric field would extend, if this is a positive charge, outward from this positive charge in all directions radially. Well, how much much force? Well, it would depend on where you are because radius is important. So KQ2 or Q over R squared. Now guys, that simplifies KQ over R squared for an electric field point charge. We got to remember that K is 9 billion or 9 times 10 to the 9th Newton meter squared per coulomb squared. We could also look at that a little bit differently from something called the permittivity of free space, epsilon naught. Now that's 8.85 times 10 to the negative 12th. If you look in your book, you'll see a few examples of that. We're not going to go too in depth with that, but it's important that you know where K comes from. 1 over 4 pi epsilon naught is another way of expressing the electric constant K. Now, for the meantime, we're going to express force per charge as newtons per coulomb. But you'll see in another lesson why electric field can be expressed in different units. I'll go over that tomorrow. But for now, let's just assume that we know that A, electric fields surround any point charges whatsoever. B, the electric fields are vector lines with direction being important. So therefore, if I'm a positive charge, electric field lines, force field lines, are extending positively and outward in all directions. If this were a negative charge, those electric field lines would be drawn inward toward the point charge. All right, let's look at a little picture to help us get this concept down a little bit better. Okay, guys, now what I have drawn on the board today here is two charges. Now I'm just using a simple proton and a simple electron. What is the electric field setup between a simple proton and a simple electron? Well, I've drawn my lines here. These are electric field lines emanating outward in all directions, radially from this proton. And this electron has radial lines moving in toward it because electric field lines are vectors. Now, what I didn't draw originally and what I'm going to draw now is a combination of those two fields. So these fields would have a vector line going like this. And these lines would connect like so. Such that field lines would move between those 2 point sources. Now, if I wanted to find the net electric field at some certain area out here, let's say I wanted to see that. Well, there would be an electric field from this place going like that, and from that place going like this. So this would be E1, and this would be E2. But you could see that there would be a net vector. A net vector. And you can see that these have points. Portions of that line are going down, and portions of this lines are going up. So really, the only net value would be a small x component of that called E total. Combining E1 and E2 for an E net field that would actually move a little bit more to the left, in this case, toward the negative electron. Well, I hope that's okay, guys. We're going to look at a few more examples involving electric fields over the next couple days. To get you started, I'm going to show you real fast the simulation program that I have up. I'd like you guys to take a look at it over the next few days. Maybe make this concept a little bit easier for you. Let's look at that now. Okay, guys, what I have here is a simulation by phet. I'll put the website up, phet.colorado. And there's a bunch of different simulations. I have the one on charges and fields. So it's going to come up like this. What I'm going to do is click a negative electron or a negative charge of -1 coulombs. As I place it out in here into the right side of the screen, you can see immediately that the electric field lines are shown as going into this point. Now let's take the situation where we just had. Let's take a proton or a +1 nanocoulomb charge. There's actually many, many, many protons. Now you can see these field lines look a little bit like what I had drawn on the board. Okay, now if I show some values here, and I take my little equipotential line, what's going to happen is it's going to show up as a voltage. So this is going to be something I can move around. Now, we're going to discuss voltage in the next couple of days. But if we just play around with where this is, we should be able to see some of those points. If you move this around, you're going to see that the values are going to change. So in the next couple of days, we'll talk about voltage and what that is in relation to electric fields. But for this, you should be able to come up with some idea of how these electric field lines look. Now you can mess around with a bunch of different charges. You can look multiple charges. You can take another charge, root it up here, and move them close. And you can see that that distorts the field a little bit. Let's take another one up here. Put another charge in there. If I put three charges together, you can see that the field shape is going to change just slightly, but the general values or the general scheme is still the same, meaning, that your lines come out of the positive charges and move in towards the negative charges. Now, obviously, with three charges here, 3 nanocoulombs, I'm going to have a much bigger force in general. But the force per unit of charge, that's what the electric field is. So obviously we're going to distort a little bit here. So I'll throw this up, guys, and you can play around with it a little bit to get familiar with it. And then I'll have an activity based on this simulation, maybe by Friday or Monday. Okay, guys, well, that'll do it for today. Just a quick introduction to electric fields. We're at the back half of chapter 16. Talking about electric fields and forces based on those electric charges that we see. So the last homework assignment, page 498, has 24, 25, and 28 available. I'd like you to look at those, and maybe we can take a look at some of those homework questions during next week's Google Meet. I will have a Google form for you to fill out after this next few, but I want to make sure you get a chance to play around with electric fields for a little bit of time. Remember, tomorrow we'll have another quick lesson, and we'll get going for the weekend. And then next week we'll resume our Google Meets, and I'll have those office hours attached. Okay, guys, have a great day. Take care of your homework, and we'll see you tomorrow.